Okay, yeah. So today we are gonna pick up where we left with the call number one. So to start, we'll have Shao give a presentation on some research that we've been doing into coming up with a new mechanism that is implementable for multidimensional fees. And then we'll go through a few proposals that came up after our first call. This is more for short-term changes, some of which we discussed in the call. And then we can have a discussion in the end on like anything else that is top of mind. I know Ansgar has some things to discuss, and then we can also open it up for others. So yeah, I'll start with the presentation from Shao.
Yeah, thanks, David. With me for 1 second, I'm gonna share my screen. Uh, could you see my screen?
Yeah.
Yep. So today I'm gonna give a talk on the multidimensional fee. Multidimensional fee, also the multidimensional gas. And uh, let me start. So basically, right now we have a single dimensional gas. And basically, the gas is a combination or a metric that bundles a various type of resource consumption into just one-dimensional number, which simplifies the fee calculations and block construction. And for gas, there's several resources contained there, like the key resource types such as the computation, the storage, and the bandwidth, and so on. So basically, the gas is a linear combination of these multidimensional resources. And for the block, we have a block limit of 30 million gas, and we're using the protocol like EIP 1559, especially for L1, to dynamically adjust the fee so that the target of block space gonna reach half, which is 15 million. But there's some limitation there. So for example, if a block were only use like one type of resource and consuming up to 30 million gas, so the safety constraint is that for each resource, if a block only use that single type of resource, and the safety of that type of resource can consume up to 30 million gas. But what we have for one-dimensional fee mechanism is like the combination of all the resources together are gonna less or equal than 30 million gas. So basically, the current model, what we have right now, is a linear combination. I only show like two dimension here, but in reality, there's a multi-dimension. If there's only like data storage and computation, that is two dimension, and the current model or the current constraint is like x1 times data plus x2 times computation is less than than 30 million than n. But in reality, the safety constraint should be the maximum of xy times data and x2 times computation, and could also consider the other type of resource. And the maximum of this number is less than n. So which also means the safety limit for one resource I is n over xi. So I also draw a graph here to visualize what we have. Like if you consider the black line, which basically means that the constraint that we have today. And if you look at the space under the black line, which is a triangle, and this is what we can have. This is like for each block, this is what we can have for the block space today. But uh, we can expand the constraint to be this this blue rectangle, and like every single point within the rectangle is also safe. So what we have for today is like within the current constraint, a lot of block space cannot be utilized, which means that within the which means that like we can have the block space within the constraint of the blue rectangle space, but what we currently have is only within the black rectangle space. Sorry, what was x? Oh, so we have x1 and x2 here. So basically, if you like how you so basically the right now the gas is a linear combination of a lot of resources, and the weight of each resource is the x. Yeah, it's also the gas cost. And so we have already implemented EIP 4844, which is a example of the multidimensional gas mechanism. So we introduced a new data structure called blob, and in the 4844, we have two resource. One is the original L1 gas, the other is the blob. And for either of these two resource, it have a limit or a target. And for the first, we are targeting at 15 million gas. For the second, we are targeting at 3 blobs per block. And for each resource, we have a separate fee mechanism, EIP 1559 mechanism to control these two resources. And there could be another type of another example of multidimensional gas that we can discuss here. For example, there's a state growth type of resource, and it basically have a long-term constraint, which means that it's okay that for each block, the 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 state size growth could be large, but what we have to but essentially what's important is we need to make sure the long-term average of the state growth is within a number, which is a little bit different from the transient resources like computation or call data, which means that for this type of constraint or for this type of resource, the EIP 1559 may not optimal for this one. And there's some literature, or we can also design some simple but separate fee mechanism that targeting at this type of resource. And 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 yeah, and we're gonna skip that page. And we have a so if we are talking at the multidimensional fee mechanism, and we want to claim that okay, it's very directly that for each resource, maybe you can have a single one-dimensional EIP 1559 to control the price or control the contraction of one resource. But there's a problem that we have for this type of transaction is that right now the transactions have an overall gas cap that the user can submit. And for each transaction, there are different sub-costs. And for each sub-call, the user or not the user, but like if you write the smart contract to call the sub-call, you can also specify their own gas limit for the sub-call. And which is like the reason is that we can reserve gas remain for the following cost of the transaction. And with a multidimensional pricing, each resource would ideally have its own limit within the subcall. But what we have for the current EVM is like we can only set one number for each subcall. So we can only set one gas limit. And there's an approach that's proposed by Vitalik is suppose that a transaction have a multidimensional limit L1 to LK with the current remaining gas G1 to GK for a subcall with overall limit S, and so what we gonna set for the limit of the subcall is just the proportion of alpha, and for each dimension, we can have a limit of alpha times a GI, and GI is the remaining gas for this type of resource. And here's one way to deal with the problem, but maybe we can also come up with the other solution here. And this is the following, like a future research direction. And we also took a little bit look at the empirical results because I don't have that much time to run the code. So I only get several point here. But what I'm doing is like I analyze the two-dimensional scenario. So we only consider the two-dimensional, which is the compute and the storage. And I'm looking at the block starting at the block number of like 20 million and one, which is on October 18th. So in one block, we just compute the gas usage of these two dimension and we scale the limit so that their sum reaches 30 million. To give an example here, if one block it consume like 10 million gas on storage, but 5 million gas on compute. If we scale it up, then we're gonna have 20 million gas on storage and 10 million gas on compute. And here's the gap. And what I want to show here is like, okay, if you like scale up the block size such that the gas reaches like 30 million, we can know that there's a gap between what we have within the current constraint to the safety constraint. Like what we have is the rectangle space, but what we can do further is to enlarge the rectangle space to the what we can do further is to enlarge this triangle constraint to the rectangle constraint, so that you can imagine for the future block size, if we implement the multi-dimensional fee mechanism, like ideally I think the block space can large as for example twice as what we have for now. And here's what we have done for this research, and there's also a lot of further research gonna be done in the future, and especially the empirical part, and also we need to come up with a fee mechanism that can really work. And our target is to have a new EIP for this multidimensional fee mechanism. And if anyone is interested in, we're very happy and open to collaborate on this research. And that's all for today's presentation.
Thanks, Shosha. I think this is good. Like maybe I'll add just a couple of things. Like yeah, Shosha has been thinking more about like some concrete mechanism, but also like this ongoing like empirical analysis. And Shosha, you can stop presenting in the meantime. This empirical analysis, like the idea is like first to get an idea. Like we want to try to estimate, okay, if we were to implement a multidimensional pricing mechanism that works, what is the impact? Like how much more throughput can we get? Like looking at like some historical set of blocks. So yeah, we've started looking into this data set, but if anyone wants to contribute on this, like you can DM Shou Chao or like myself, and I can also connect. Yeah. So next up, we can switch to more short-term changes. I think Jacek wanted to quickly show their new proposal for repricing that they came up with after our last call. So
okay, yeah. So last time we spoke about our methodology, how we came up with the numbers. Now I want to talk more about, let me just zoom in a bit, what the actual proposal is. So I'm still finalizing EIP, so I'm gonna show you this table here, but I think it's even easier to read from this table. So what we have here in this column is the current gas, and our proposal on the right. In the middle, we have something that we discussed in the last meeting as well, so the fractional gas. This is not our actual proposal, just for you to see what would be the more real cost of each opcode. So in general, our proposal aims to lower the computational cost. So leaving the storage and core data cost at the same level and lower all opcodes and make them more realistic based on our benchmarks. So as you see, most of the simple opcodes, they go from whatever they were to 1. There are a few exceptions from this law, but this is just because these opcodes turned out to be more computational complex. For the well, we have a dynamic cost. We also propose some new costs. So you see, for example, here the exp would be slightly cheaper, or actually quite much cheaper. The KESAC would be slightly cheaper. So our benchmarks didn't show that this is actually an easy opcode. If we move further down, we see these are we turn it all to 1. And here, when we have all the memory operations, we usually have a cost memory size plus the memory expansion cost. So in most of these cases, we leave it very similar to what it is, but make it more in line with the other opcodes. But we will talk about the memory expansion cost and accessing address warm and cold addresses later on. Okay, so these opcodes all go to 1. I'm just looking at some more interesting stuff here. The new tload, tstore opcodes, they are in fact much cheaper than initially anticipated, at least according to our benchmark. So this should put them more in line with other opcodes. The memory copies, okay, the log cost. Now, this was more tricky to estimate what the actual cost is of logs. So this proposal takes mostly computational cost of logging plus little bit of storage, but I think I need to run more analysis on logs. to be more sure that this proposal makes sense. Now, when we go to create on a surface, there's no change, but the memory expansion cost will be well. That's okay. I was wrong. Very small changes, but mostly it's the same. The memory expansion cost is slightly different, which is the same for all the calls. So the formula is the same, but the memory expansion and the address access cost will be lower. I show you in a moment. But first, let's talk about precompiles. So EC recover, even though we reduce everything else, EC recovery stays at the same level. Those opcodes are not used much anyway. But also the same goes for the mode exp, but I think Martin will present more in-depth analysis on this one in a moment. What we can say, the EC art is actually more expensive than anticipated, and to be fully backwards compatible, we actually propose to leave the cost at the same level, even for the actual cost is much higher at the moment. There might be a little bit risk involved with this, but it's the same as it is at the moment anyway. Okay, let's talk here about the memory expansion cost. So at the moment, what we do, we pay for each new slot allocated. We pay 3 gas, plus we pay the expansional cost. So the more we allocate, the more we pay. Our proposal is because the analysis show that the memory management is cheaper than the current cost. So our proposal is simply to ditch the per slot cost and only leave the expansional cost, meaning that the first 22 slots of memory will be actually free to use, and you only pay for the allocation when you exceed it. Another thing is the address accessing cost, and here we recommend to significantly reduce accessing warm access cost. Our analysis showed that this is very well, once the address is warm, it's very well cached in most implementations, and we can lower it to really minimum. Also meaning that any precompiles will be cheaper, because you still pay, at the moment, you still pay 100 gas cost for each precompile. We propose it to go to 5. So this is the initial proposal. I will try to finish my EIP soon, and I will share it with you.
Thanks, Jacek. I don't know if there are some comments here. Maybe we can reserve like a few minutes if there are a couple of questions.
I see opcodes priced at 0, which it's 0 plus some cost, so there will always be some cost associated with this. Log costing, that's true. We need more thinking and analysis on the log as well. The next question, I would always generally round up. Yeah, it's up to us, Lily, how we want to do it.
I see. So Marek, and the question.
Yeah, so I have a question, because we benchmark it in isolation. So for example, we took just add opcode, but we know that in EVM we will be doing the loop. And my question is if we are concerned about this, if this is good enough representation of the truth that will be happening on the EVM level, because if we,
so
so
our methodology, in essence, we try to exclude any factors like, caching, warming up of EVM or the preparation of something. So when we benchmarked it, we didn't took just one opcode and run it through EVM. We took a series of opcodes, including some random data, and then we extended the number of opcodes under the test in order to see how much the execution time increases. And this is the thing that is basis on our, which is the basis of our proposal. So as much as possible, we try to get the true cost of executing an opcode.
Okay,
thank you.
and
Makes sense.
The warm access cost, is that both like balance and SS load?
The balance account code and well, let's see where we have anywhere where we see the address access cost. So code copy, code size, code hash, for example. All the calls.
Okay, what about S load and T load?
T load
Okay.
but doesn't actually have the dynamic cost, so it's always static 100 for T store. For the S load S store, I don't have it here, but it goes with the same way. So the cold access stays the same because it's the storage cost, while the warm access is significantly lowered because that's the more computational cost.
Cool.
And Lucas?
Yeah, I don't think we can just say that some opcodes because they're not often used, that we can ignore it, because that could potentially cause open attack vectors, right? So we potentially need to consider that each opcode can be very heavily used in the block and price it based on that.
We didn't ignore any of the opcodes or precompiles. We ran the calculation on everything. What I mean, some opcodes matter less for a normal user, but we still keep all the security in place. So this proposal here does reflect the true cost of computing this precompiles.
And Ben, you want to go again?
The transaction cost at 21,000. That's effectively, is it not a warm access cost because it's right up front in the transaction and the to and from. So does that count?
It's a good point. I wouldn't touch transaction cost here. So I want this EIP to focus on opcodes only. The reason is that the transaction makes some addresses warm, and you have to pay for making them warm. Yeah. So hence the cost of 21,000. We can look at what the transaction cost is made of and maybe decide to lower some of the elements. but that's completely different discussion.
Okay, so I mean, it sort of comes into access lists cheapening. So if you're cheapening access to warm based on an access list, you're effectively also doing it with to and from.
Oh, in that sense, yeah, true.
What is the baseline here?
So the baseline, so we had to rescale the results, and what I used for the rescale was the average cost of basic arithmetic opcodes, so from 0, 1 to 1D. This was the basis of rescaling.
And one more comment from my side. When I see results from pre-compiles, they're like very different from what we got in our tooling. So we need to, I don't know, chat about it. For example, I see that easy pairing will be potentially less expensive, and this wasn't the case in our benchmarks, for example. So I think it's good that we have two toolings and we have to compare the results together.
Yeah, definitely. We need to compare the way we came up with this and our benchmark methodology. Yeah.
And Paul?
I kind of have the same question, and what Marek and Łukasz discussed, that yeah, I think we need to establish what is like the security goal here, and I'm sure this is pretty well defined so far, because like what Jacek has showed is like they kind of try, to my understanding, they try to kind of readjust the numbers by like kind of self-tuning, so they compare what they are and how they differ from each other. And what I wanted to do with this is to kind of verify it from the other side, that we know what is like the safe limit that we aim for, and in case we find example that actually crosses this limit, it means we need to modify the numbers we have. And I'm not sure if we have a good way of actually setting up this limit up front, because it kind of affects many things in the same way.
We don't know what is the right or safe limit or cost. We can only try it and see how it works. Yeah.
Well, I mean, can we have a number, something like none of the blocks should be executed longer than 1 second, for example? I think that's the kind of boundary we want to establish, and we can move, like, modify the numbers within this boundary. I think that's much easier to work with than like self-tuning the gas by seeing the other gas numbers, because yeah, I kind of want to know like what is like the safety boundary here. And it kind of, it also goes back to the previous presentation when we kind of to be moving, like optimize within some like space that we have established for security. But before we establish this, like the boundaries of this space, it's really hard to actually check if this number is kind of within safety margins or not, because we don't have the margin yet.
So the methodology, never mind, was using is establishing some hardware requirements, and I think we're using fairly low-level hardware like Intel NUC, I don't know if 10th gen or something, and then creating a block, filling it all with opcode or a precompile, executing this block and measuring megagas per second on this machine. So, and then we kind of aimed at thing at least at 60 megagas per second or more on this machine. So that's kind of was our ballpark of doing stuff.
Interesting. So it looks there is a couple of interesting things to follow up. Like one is maybe like doing this exercise of like establishing the safe limits. At least have like some logic that we have as reference. We agree as reference. Yeah, and then the other thing I was thinking, maybe it's also a good thing to follow up after the call, like the comment on like for precompiles. Now we have like two tools and we can do some comparison. I think this is really good, actually. Cool. I think this was great. So Jacek, thanks. And yeah, really excited for the progress. Yeah, so I think next we had Marcin who wanted to talk about their ModX proposal.
Yes, sure. Let me share the screen. Okay, so I would like to present EIP 788 so ModX the gas cost increase. Right now, ModX is priced according to EIP 2565, and unfortunately there are underpriced scenarios for its resource consumption. And by modifying ModX pricing in this EIP, these scenarios are covered, and we are doing it with minimal impact on real-world usages. Our target here is to make all ModX scenarios at least as fast as EC recover precompile. So all the worst performant edge cases will be performing at least as fast as EC recover. So we have this EC recover as our reference, and on this machine it was performing at about 60 megagas per second. And as you can see, there is a lot of ModX scenarios which are performing way slower. I would like to focus right now on the ModX, one of ModX common cases. It's a case from mainnet, and 200 is current minimal price for using ModX precompile. And in the scenarios, it's performing more than twice too slow according to EC recover. So at this point, we know that we need to increase minimal price. And there are also other cases, but I will talk more about them later. Current ModX pricing formula is a function of multiplication complexity and iteration count. Multiplication complexity is just depends on base length and modulus length, and iteration count depends on exponent. Our proposal is to change do three changes to this pricing formula. First is to increase minimal price from 200 to 500, and second one is to increase exponent cost only for the cases where exponent length is bigger than 32. And the third modification is to right now the multiplication complexity is just square root of words. and we want to keep it, but only if max length is equal or lower than 32 bytes. And if it's bigger than 32 bytes, then we are doubling the cost. And thanks to that modifications, like all the cases are performing better or similar to easy recover. And we also did .NET benchmarks. Our reference on is still easy recover, and on this machine it's performing at 50 megagas per second. There are in current pricing formula, there are other price scenarios which are performing below it. But there are also scenarios that are performant enough, and these are scenarios like cases where all parameters are lower or equal to 32 bytes, so we can consider them as real world scenarios. And thanks to this changes in pricing formula, we are adjusting the worst cases, and I can say that these red rectangles are in historical usages on mainnet. It's less. It's about 0.21% of all usages, so really not much. And we are adjusting price of it, and price of this common cases is untouched. It's like one group of common cases. Second group is this ones which I told at the very beginning. So where the minimal price is just minimal cost is just too low, so we can do nothing nothing other than just to increase it. And these two modifications are affecting only 0.31% of historical usages. So it's our proposal, and there is also another approach to ModExp repricing. It's ModExp EVMification. It's like proposal from Vitalik. It's like 7666 is about identity precompile, which is removing identity precompile and putting into the contract a short piece of EVM code with the same functionality. And as Vitalik writes, in the future we can do the same with ModExp. So someday Ethereum will drop ModExp precompile and probably EVMify it. And we need to decide if you want to go straight for it, so for final solution, or postpone it, and for now just make ModExp pricing appropriate. So using our EIP and, for example, 7823, so set upper bounds for ModExp. And that's all from me. There are any questions?
Thanks, Martin. Yeah, we can take a few questions. There are.
I think for changing ModEx to a smart contract, we need EVM max. Otherwise, the cost would be like 100 or 1,000-fold more. I might be incorrect there. I assume that'll take longer.
Yes, I just I know that such proposal is it was proposed by Vitalik, but probably it's like we are not ready for it. So it is why we prepared this EAP. Are there any more questions?
So there's a good question from Tony in the chat that would 200 to 500 increase in base, would it affect most of ModXP or not? Because it's a bit confusing.
Yes, I don't have calculation for it, but it's like a big part. It will be about 40 to 50% of all usages. But if we want to perform as fast as EC recover, it just there is no other way than to increase it. So to be clear, all the cases which at least one parameter is bigger than 52 bytes, it's just only 0.3% of historical usages. But the ones with minimal pricing, it's a lot. So I need to do calculation for it, but it will be about 40-50% of all usages.
Okay, thanks again, Marcin. Yeah.
Okay.
And now I think Tony wanted to share something. I don't know if presentation or just like heads up on his new proposal.
Yeah, thank you. Hi, everyone. I just wanted to quickly use the opportunity to share this recent ETH research post on block level warming with all of you. Let me post it into the now. Right, and it's not only block level warming, but there's also a second post on block level access lists. And first, for block level warming, the idea is to keep a set of access storage slots over the whole block. And basically, the first person that accesses a certain storage slot has to pay, and everyone else gets the warm cost without doing any refunds at the end. You can also see on ETH Magicians, there's also a thread on the whole topic. There are some problems. For example, one of the concerns that were raised is around parallelization. Another one that was raised on ETH Magicians is around block level warming acting as a disincentive for access lists. And then the question is how to best approach the whole thing, because there are a lot of cross interactions with access lists. And as soon as we do something like block access lists, where the block builder has to put all the storage slot that he is about to access in that block into the block header, then the question arises if it wouldn't be smarter to directly add the values too. And yeah, so I just wanted to bring that up, and happy to discuss that a little further.
Thanks, Tony. Yeah, I think it's a really cool proposal. Is there any question?
So if someone wants to think about that, the main challenges are parallelization and how to make it aligned with access lists. Because the problem with block level warming and access lists right now might be that you have less incentives to put something on your access list, because the chances that this slot is already warm when it comes to your execution are higher. And then, of course, you would pay for the access list and already have a warm slot.
So to be honest, if we have parallelization, I don't care that much about access lists, because I can already amortize that cost, and access lists don't give me much for speeding up the block. But yeah, if it messes with parallelization, it's really, really bad, in my opinion. And maybe one question: how does this work with witnesses, like vertical witnesses or any others? Because those will be like in a block, right? So potentially, does it solve something? Does it make it harder, easier?
Yes, I understood it. So for me, I like thinking of the vertical witnesses as just like block access lists on steroids. So it's just in addition to the storage slot, you would also add the value. And yeah, there are some arguments for doing so. I think the average storage slot is only around 8 bytes or something. also there are arguments to directly add the values too if we want to do block level access lists where the proposer, the builder, has to specify all to be accessed slots upfront. Ansgar?
Yeah, I just wanted to say, yeah, with the access list as well, there is there was this ERP draft from a bit over a year ago that I put in chat from the card abstraction group people as well that actually never was turned into proper ERP. But I personally kind of like at least a part of their design where they basically try to avoid this issue with the access lists by basically making them the mechanism for that, and then you do equal refunds, and that way basically you actually instead of ending up disincentivizing access list, the mechanism ends up incentivizing access list usage, which is actually quite nice.
Yeah, something that gets us closer to that scenario would be very beneficial, because if the more addresses we get into the access list, the more it will be pre-warmed for all. And yeah, so there are also some ideas. I think Peter mentioned some ideas on ETH research. I'm not sure if he's in the call, I guess not. About processing them not on a transaction level, but maybe after the whole execution, processing some refunds for access lists post-execution. That sounded very interesting, but yeah, I still have to get my head around it.
Thanks, Tony. Yeah, and I think Ansgar has some thought on like estimating gains from repricing, like something we also discuss in the multidimensional case, like getting an idea of like how much gains we can get.
Oh
yeah,
yeah,
the gains
yeah.
are also in the ETH research post. So it's basically like, imagine we only have warm costs, then it's around 36%. So we pay 36% of our gas for warming storage slots. And I think around 20% of those is for unique storage slots, or let's say half of it, right? So half of our storage slots are only used by a single address. Sorry, single transaction.
Yeah, right. Because for savings, of course, you would only get savings where there's actual overlap, because otherwise you still have to warm them at some point. I think long term we can in general also like consider like how could we more cleverly treat state where basically you kind of if say every access is declared somehow statically with access lists or some other way of attaching metadata to the block, then you can basically start loading them all from disk at the beginning of the transaction. And if you do that in a clever way, maybe in the right ordering, you can basically keep loading while you already execute. And then as long as somehow basically you only ever access them after they already were loaded, basically if you find a good way to basically balance that you access them not at a faster rate and then you're loading them, then in a way you basically never block and wait for storage, and then you can basically use that time for actual compute or whatever else you'd want to do in the block, which would be quite nice. But you need like a more sophisticated mechanism for that.
Yeah, I agree. And also it's very beneficial for parallelization. So I would say the more we get into access lists, and even better if we enforce them, the better for parallelization. And also I think Dankrad had some very high numbers of the efficiency gains we could get there because of parallelizing discretes and also execution.
Right. Yeah, I mean discrete you can't really you can't parallelize in that sense, right? But basically, yeah, you could basically get more compute in if you basically have transactions that in parallel would want to do some compute. And you can make it so that you basically spend as much of your time as possible actively loading things from disk. So yeah, there's definitely a lot of improvements we can do.
I mean, you can parallelize in a different way of thinking about it, in that the SSD can do, 16 or 32 parallel loads. But the issue, so you can convert storage load latency into throughput. But the issue we have with the EVM is you don't know what the next one is until you run the next instruction, until you run the next instruction. So with access lists, you could load all the data in parallel, whereas at the moment we have to load the data sequentially.
There's an interesting nuance here. I mean, I think we're running up on the end of the call, but this is an interesting topic. And I think in general, like having maybe a more focused breakout or something at some point on like more just storage access and parallelization and whatnot would be really interesting. But like the nuance there being that like access lists themselves give that benefit also to the builder, but you can basically get the benefit only to verifying nodes if you want to by just having the builder afterwards create a full access list for the entire block, right? And then it doesn't even have to be like a stateless witness where it comes with the data, just the access lists. And then that way anyone else receiving the block can basically start loading. And then it's not sequential loads where you basically always have to wait. You can basically do the entire loads for the complete block in parallel at the maximum possible throughput from your disk. Which in principle, under the right circumstances, could give you a big boost.
Right, and kind of, if we leave away the values, this access list still remains quite small. So I think on average, if you kind of naively sum up addresses having 20 bytes, storage slots having 32 bytes, then we end up at around 40 kilobytes per block if you put all addresses, all storage keys into it. So it's not that big. I'm not sure how much bigger it would be if we add the value here.
Yeah, so my point would be, but yeah, we would be doing something here, but that we would throw away when we do witnesses, and witnesses give us like no storage slot cost at all on the access. So I don't
Exactly,
really
yeah.
see, it's a stopgap solution that I don't really see worth investing in.
Cool. I think it's time to wrap up. Thanks everyone for joining. There is a few things that came up that we may want to follow up. I think we can send some follow-up in the channel, and then we can also work around scheduling the next call like in the channel as we make progress on these. But yeah, thanks again, everyone.
Thanks, everyone. Bye-bye.
Thank you.
Thank
everyone.
you.
Thank you. Bye.
Bye.